Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. Tonight, we will embark on another space cruise. We are well aware this is a favorite topic for a lot of you. But this time, we are not going to a particular planet, a star, or a galaxy. We are visiting representations of the cosmos theories. We are looking for something that may or may not actually exist, the center of the universe. On our way, I'll tell you about historical representations of the cosmos, about modern scientific theories, especially the Big Bang Theory, the apparent expansion of the universe, and the notions of time and space. But don't worry at all if you are unfamiliar with all these concepts, with physics or astronomy. It's all going to be easy to follow and understand. We will advance progressively. We will work with analogies and examples, and all you need to do is let me guide you through this journey. But first, I would like to take a few seconds of your time to let you know that we have a Patreon page for those of you who wish to and can support this project. Get more of it and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3.50 per month, but it doesn't mean you will get less. We let people contribute what they wish to or can, and everyone gets everything that is on our page, because the world is a better place when the sun shines for everyone. You will gain access to several exclusive episodes, and also all our episodes with and without background sounds. We offer advance releases to our patrons as well. We have added links to Patreon as well as links to different streaming options, which may be better suited for you. You will find a link in the description of the episode. But before we begin, let's take a moment to center ourselves. You may sit or lie down and, if you wish, close your eyes. Let go of any distracting thoughts and daily worries. Adjust your posture until you find that perfect spot of comfort. Take a deep, refreshing breath and exhale slowly, noticing how your body naturally relaxes. Feel how the tension dissolves from your shoulders and neck. Allow your facial muscles to soften. Release your jaw. Let your hands rest gently and feel your legs becoming completely relaxed. As you find this state of calm, I'll guide you through our exploration ahead. We are about to take off for our biggest cruise ever, because this time we will not just go to other planets and galaxies. By the power of imagination, we will travel billions of years into the past to explore the nature, the size, and the history of our universe, or at least what the current state of science can tell us about it. Because as usual, this kind of exploration always requires a great deal of humility. The only solid truth here is that we know little and have to make hypotheses or ask questions with the maybe limited tools of observation and understanding at our disposal. Anyway, let's get started. So, where are we heading to find the center of the universe? Our ancestors believed that it was Earth or the Sun, or much later, the center of our galaxy. But we know today that these hypotheses don't really work in a scientific way. A first answer to this question, if we follow the Big Bang Theory, is that we don't need to travel anywhere to reach the center. It's here. Not because Earth is at the center of everything, but because any point is as good as any other. There is no center to the universe we live in. What does this mean? You probably know the concept of the Big Bang Theory. At some point in the past, billions of years ago, the entire universe was concentrated in a single point. And suddenly, like an explosion, this point expanded at speeds and levels of energy that defy imagination. This is not a bad metaphor, but it leads to a common misconception about the Big Bang that pictures it as an explosion in the void, as if the void of space pre-existed the Big Bang. If that was the case, the universe would have a center. In an explosion, the central point is the hottest point from which matter and heat are projected in every direction. But this is not what the Big Bang Theory says. The explosion did not take place in space. It was an explosion of space. What we call the void of space is part of the universe and enclosed into it. It is not something external. So rather than an explosion, an analogy that works better here would be one with a balloon that is being inflated. It expands in every direction. But imagine that the universe is not the ball formed by the balloon. It is its surface, just the surface. Now, if we consider this spherical surface and ask ourselves where the center is, we would say that it can be any point. All points can be the center, because relative to them, all other points are moving away as the balloon inflates. Or simply put, if I give you a soccer ball or a basketball, you cannot point to one particular point on this surface that would be its center. We will talk in more detail about the Big Bang Theory, what it says, and how it became the prevailing model describing the appearance and expansion of the universe. But before that, there is also a wealth of historical representations and other more modern theories to talk about. So let's explore this from the very beginning. Until the 20th century, the questions of the age of the universe, its size, or its limits were not much studied by scientists. This question was considered to be in the field of metaphysics, literally what is above physics and cannot be grasped or described with scientific laws. A lot of different traditions and religions around the world provided answers about how the world had been created and when, or more exactly, the earth. Whether it was seen as a world among others, a ball or a disk, what the ancients called the world was earth, and the idea that the sun and the stars revolved around it was not really questioned. But this physical horizon started to be put in question with the progress of astronomical observations and the realization that Earth was an object in space, among others, that could actually be much bigger. Over time, new models put the sun at the center of the universe, like that of Copernicus in the 16th century. and they made Earth a planet among others in the solar system. Then the existence of our galaxy was progressively revealed, and in the 19th century, the Milky Way was often believed to be the universe itself, until it appeared that our galaxy was just one among others. So, over several centuries, the size of the universe, as we perceive it, has increased dramatically, and our place in it as human beings living on planet Earth has been reconsidered in a way that is quite humbling. But another assumption in the late 19th century was that the void in which the galaxy was floating was limitless and ageless. It was eternal. This was not a theory or something people argued much about, just a hypothesis that answered questions about the frontiers of the universe. In a sense, this assumption was comfortable, because if the universe was eternal, then there was no questions to ask about its formation, its history, or its age. And if it was limitless, then this eliminated the question of what could be beyond its limits. But this had not always been the case. So how did men picture the cosmos, the universe, and our place in it throughout history? In many different ways. All civilizations formed their myths of creation, in which different gods were the artisans or sometimes the products themselves of the world's creation. I have told you about some of these myths in recent stories about Greek, Norse, or Egyptian mythology. But maybe the Greeks were a bit different in their approach because they introduced something else. The idea that natural phenomena were not just things to be observed or attributed automatically to the gods, but also things that could be understood and used for a better comprehension of the world. The Greeks didn't define the scientific method as we define the concept today, but they certainly elaborated its premises. Other cultures around the world also had an elaborate knowledge of astronomy, for example, like in Mesoamerica or in China. But it didn't go in the direction of observing planets, the sun, and the stars as physical objects that could be measured and speculated upon to better understand the harmony of the world as a whole. It doesn't mean the Greeks figured out everything. Far from that. To them, the world had to be geocentric, that is to say, with Earth at the center and all other objects in the sky moving around it. This was a rather obvious observation to our ancestors. They saw celestial bodies move above their heads and come back year after year to the same position. They had no reason to imagine that Earth itself was just one of them. And so, the Greek world adopted the concept of Earth at the center of a universe, with celestial objects placed on another, larger sphere that rotated around our world. This is how Plato, the philosopher, described the universe in the 4th century BC. The Greeks had found through deduction that the world was round, even though this was not intuitive or visible. This shows the power of their deductive approach to nature. They were ready to adopt a vision that was not immediately obvious to their senses because it was logical, and the same logic made them question this description of the universe, with a single celestial sphere carrying the planets and stars around our world. They observed that something didn't work with the motion of the planets. They sometimes appeared to move backwards in the opposite direction to the stars and the constellations the stars formed. We know why today. Earth is in motion too, in the solar system. So above our head, the planets of the solar system can seem to go backwards on their orbit, not because they do, but because our vantage point is also moving, which can create this observation. In astronomy, this is called retrograde motion, the apparent change in the movement of a planet through the sky because of its relative position to Earth, and how both planets are moving around the Sun at the same time. There was no way that all celestial bodies could be attached to this single external sphere then, and they came up with another explanation, also based on observation and deduction. Since the stars and the planets were not synchronized, it had to mean that there were not one, but several celestial spheres carrying objects in the sky. Up to 33 different spheres of larger and larger diameter, rotating around us. Interestingly, the axiom that we were the center of the universe was not much questioned. It was taken as such an obvious thing that most of the Greeks didn't think about the possibility that Earth itself was moving. Most of the Greeks, because there were exceptions, for example, Aristarchus of Samos, an astronomer from the 3rd century BC, who had a remarkable intuition. He placed the sun at the center of the universe and made Earth a planet among others. But his vision didn't stick and was mostly ignored, even though it was, in a way, more pertinent scientifically than the geocentric universe and its spheres turning around Earth. But however flawed this concept of multiple celestial spheres rotating around our planet was, there were also interesting and promising ideas in this depiction of the world. By considering that every planet was carried by a different sphere, the concept of orbits in space appeared. And overall, this depiction of the motion of the planets, the stars, the sun, and the moon above our heads was quite satisfactory at the time. So in the West, it remained the dominant scholarly description of the universe, not just for the period of ancient Greece, but for many centuries, almost 2,000 years until the end of the Middle Ages. More significance and elements were added over time to this multispherical system to give it more spiritual meaning and connect it with natural sciences. Aristotle, for example, divided the universe into two parts. Everything up to the space that carried the moon belonged to the changing and imperfect world where life, decay, and death existed. This world, our world, was made of the four elements: water, air, fire, and earth. Beyond the lunar sphere was the world of the high spheres, with the planets, the sun, and the stars, where everything was perfect and eternal. The Christian tradition also added elements to this world view, especially a friar of the 13th century called Thomas Aquinas. He added yet another sphere beyond the last one where God would have resided and from where he could embrace the entire creation. Angels lived in the solar and planetary spheres. The degree of divinity decreased as one moved down closer to Earth. The purgatory, a notion that had been introduced in the Christian tradition during the Middle Ages, and our world were part of the sublunar sphere. You see that there is still the influence of Aristotle in this worldview. And below our feet, even lower in the ground, was where he placed hell, the land of evil, where bad souls resided after their terrestrial life. Men were placed in between the heavens, the high spheres of the divinity, and hell underground. Almost 2,000 years with a stable description of the universe, and one that had been embraced and completed by theologians for centuries. This carried a lot of weight, and it is important to understand the reluctance to reject it, not just from the Catholic Church, but also many scholars of the 16th century, when new theories were put forward. Because these new descriptions of the universe could not just be scientific speculation. They shook centuries of tradition and the credibility of all these generations that had embraced this Greek and then Roman and then Christian system. The first and probably the most important intellectual revolution of the modern era when it comes to the description of the cosmos happened in 1543, when the Polish mathematician and astronomer Nicholas Copernicus published his description of the cosmos as a new system that put the sun at the center of the universe instead of Earth. As he explained, the movement of multiple planets around the sun in a way that was very convincing. Embarrassingly so for the community of astronomers who knew about the movement of planets. Placing the sun at the center of the universe instead of Earth had profound implications, intellectual, cultural, emotional, spiritual even, because it also meant that humans were no longer at the center of the universe, and maybe not even at the center of creation. This heliocentric hypothesis, with the sun in the middle, was actually not entirely new, as we have seen before. It was formulated in ancient Greece, but at the time it hadn't been successful enough to make a cultural or conceptual impact. In Copernicus's system, the theory of spheres was not rejected either. He just supposed that Earth was one of these spheres, and the universe was much larger than thought before, because to him, the last sphere, the one that carried the stars, stood still. It didn't move. And it was the motion of Earth that now explained the apparent movement of the stars in the sky. But to make it work, to make it fit with observation, he had to place the last sphere much farther than thought before, beyond the limits of the solar system. So at once humans were ejected from the center of the universe, and the universe became much larger than ever imagined. That was controversial. But it took decades until the early 17th century for the various churches, Catholic and Protestant alike, to attack these new astronomical theories, especially at the time of Galileo, another well-known and major astronomer. But attacks were not just on theological or spiritual grounds. Scientifically, Copernicus's system seemed to work well, but it had a few holes. One that served as a starting point to a Danish astronomer, Tycho Brahe, was the observation of comets and the supernova he saw in 1572. We are 29 years after the publication of Copernicus's system. He saw what looked like a new star in the sky, so shiny that it remained visible for a month, including during the day. He couldn't know it, but this was certainly a supernova in the constellation of Cassiopeia, the death of a dying star that liberated the energy of billions of suns in a few days. And this happened millions of years before the observation, the time for the light to reach Earth. But to him, if a new star could appear and disappear like this, it meant that the sphere of stars was not as immutable and perfect as thought since Aristotle and even in Copernicus's theory. The sphere of stars could change. Another thing that caught his attention in 1577, 5 years later, was the appearance of a great comet visible from Earth, and its trajectory could be observed. The trajectory formed an ellipse that seemed to cross several spheres, and these spheres were seen as material. They had to be solid to carry the various celestial bodies like the planets. Otherwise, the planets would have fallen. At the time, the concept of gravitation and the idea that bodies could float in space was not yet a thing. But if the spheres were solid, then how could a comet cross several spheres on its trajectory? Something was off. And even more, in the early 17th century, new instruments to observe the sky revealed that not only the moon seemed to have a geography, but other planets had satellites. This was when Galileo observed for the first time the four main satellites of Jupiter. In about 70 years since the publication of Copernicus's work, the old representation of the universe had crumbled, and new theories were popping up to explain the new observations made. On this path, the works of Galileo, then Kepler, Newton, very importantly for gravitation that finally resolved the problem of these spheres that could definitely not be material. All of this made modern astronomy emerge, a science that was now primarily based on ever more precise observation. And when it comes to the field of cosmology, it had huge implications. Cosmology, the studies of the description, the origin, and evolution of the universe, became a branch of astronomy or astrophysics. As a science, it was separated from tradition, religion, or myth, and it took decades. But this is another consequence of the intellectual revolution initiated by Copernicus's work. But due to its subject, cosmology has also connections to other disciplines, to philosophy, to other branches of physics, like particle physics. As we are going to see, the Big Bang Theory is an attempt at bringing together astronomy, the observation and study of the various bodies in space, and particle physics. So, after this little historical overview, we are now back to modern times and the march to the formulation of the dominant theory that describes the history of the cosmos. I told you that new instruments of observation, new telescopes had appeared at the time of Galileo in the early 17th century and allowed these observations. Technical progress has continued unabated to the present day, and in the 18th and 19th centuries, ever more bodies were identified in space, farther and farther from us, which also invalidated the heliocentric model. I already mentioned the discovery of galaxies and how, in our perception, the universe became bigger and bigger over the past 2 centuries. That was in the story about galaxies, so I won't repeat all of this. But what interests us here is how theories about the cosmos evolved with these discoveries. As I mentioned at the beginning, by the end of the 19th century, the old theory of spheres was long gone. And even though this was not proven, a common assumption now across the scientific community was that the universe was limitless and eternal. It had always been there, it would always be, and it was also static. In the first decades of the 20th century, it began to be understood that these distant nebulas that were supposed to be maybe island universes or clouds of gas were in fact other galaxies like ours. The central figure to the discovery of the multiplicity of galaxies was Hubble, the American astronomer. And something odd was noticed. These galaxies, especially the most far away from ours, seemed to be receding in space. They moved away from us. This was impossible in a static universe, and so a hypothesis was formulated in 1927 by a Belgian physicist, Georges Lemaitre. If objects were receding in space in every direction from our vantage point, it had to mean that the universe was expanding. In 1931, he went even further and suggested that if this expansion was projected back in time, then the further in the past, the smaller the universe was, and there even had to be a time in the past when all the mass of the universe was concentrated into a tiny single point. In the 1930s, Einstein's theories about time, space, energy, and matter were already very well known, and the concept that they were linked was admitted. So it meant that there had been a time when suddenly the fabric of time and space came into existence, when this tiny universe began to expand. This contradicted the steady state universe conception that was preferred at the time. And initially, the idea that the universe could have a history was rejected by many. Arguments against it included the fact that receding objects could have other explanations, so that was a necessary hypothesis. I'll tell you more about these alternative theories later. And also that the beginning of time was re-injecting metaphysics or religious concepts into cosmology. Georges Lemaitre was also a Catholic priest, which probably enhanced the perception that the Big Bang Theory was an attempt at bringing together modern astronomy and the Christian belief in the divine creation of the universe. So in the 1930s and after, other theories that are now called non-standard because they have been rejected by the vast majority of experts and cannot pass peer reviews were formulated. But in cosmology, non-standard doesn't mean necessarily false. A standard theory is a widely accepted one because it is backed, theoretically and empirically, by observations that fit with the model's predictions. New theories are non-standard until they are validated, but sometimes invalidated. Old theories do not disappear entirely. They keep a small core of supporters, despite contradictory observations or flaws that made the scientific community reject them. When Copernicus published his main heliocentric theory, it could have been called non-standard in the sense that it went against the consensus. Then it became standard, but it didn't make it true either. No one puts the sun at the center of the universe anymore. And you remember that Copernicus didn't reject the theory of spheres, which was abandoned later. Einstein's theories were also non-standard when they appeared. So this whole movement with theories that emerge as an explanation, a new angle should be seen as part of a process. Now scientists and the general public are also human beings. The creators of a theory can be emotionally attached to it. There can also be appeal in holding non-consensual positions and getting a form of reward from it, from a sense of self-worth to the opportunity to join a community. So theories do not always die entirely, even when the scientific community as a whole moves away from them and ignores them because they are not backed by evidence or have been invalidated by new observations. Theories have to compete and prove their worth for their place in the sun. The theory of an initial Big Bang, when and where everything was concentrated in a single point, a singularity, began to gain more supporters in the 1930s and 40s, but the scientific community remained very split. On the other side were supporters of a steady state universe. A new steady state universe was formulated to explain how the universe can be steady despite objects receding. In other words, to explain how the density of the universe can remain the same when galaxies are farther and farther apart. This theory posited that new matter was generated, that there was a matter creation field that inserted matter into the universe to maintain a constant density. Why not? It is certainly not harder to imagine than the concentration of the entire universe into a single point. For 15 years, these two theories coexisted. But the Big Bang Theory won thanks to the observation that its predictions worked. In particular, the concentration of the entire universe at the start would have implied that at the early stages of the universe, when the atoms began to form, there was a transition phase that should have left a trace, a cosmic microwave background, like a kind of white noise that would exist everywhere in the universe. It is not noise, of course. It's a faint radiation. This remnant or relic radiation was detected and measured in 1965, and it was a major game changer for the Big Bang Theory because it corresponded to its predictions, and this microwave background had no other known explanation. From this moment on, the alternative theories were progressively abandoned, and the Big Bang became the dominant, the standard approach to the description of the universe's history and its expansion. It fits with observations. It made accurate predictions, but it doesn't mean that the theory explains everything when it comes to matter in the universe. In the current state of cosmology, there is no theory of everything that would explain every single observation. Here again, there is more about this you can listen to with topics like dark matter in the story about galaxies that you can find in my library. There are still alternative models to the Big Bang Theory, or complementary models being worked on that are based on new hypotheses for a steady state universe. For example, one that supposes that the universe could go through successive phases of contraction and expansion, and we would be in an expansion phase, explaining Hubble's observation of the galaxy's receding. But these are no longer mainstream, and the Big Bang is the standard theory since the 1960s and 70s. Many attempts at the imagining and describing a different cosmology have been made in the past 100 years. More than a dozen looked serious enough to deserve conversation. The holy grail for cosmological theory is to explain all observations made. That includes faraway galaxies receding, the laws of physics that seem to work well, like the existence of gravitation and relativity, the different forces that are observed with matter from very small scales to very large ones. Hypotheses have been made to explain or challenge observations. One such hypothesis, for example, is called the tired light. What does it mean? I told you earlier that one major observation that participated in the understanding that the universe was most probably expanding was Hubble's observation that galaxies are moving away from the Earth at speeds proportional to their distance. The farther they are, the faster they move away. You remember the image with the inflating balloon that I talked about at the beginning. If we are a point on the surface of this balloon and it's being inflated, other points on the surface will move away from us in every direction, and the farther away they are, the faster they move away. But it is not that simple when it comes to measuring the velocity of galaxies that are millions of light years away from us. How do you know how fast they travel when they are just tiny points that are invisible to the eye and can only be detected by telescopes? Hubble's solution to measure their velocity was their redshift. The redshift is an increase in the wavelength of light that we receive from them. It is called redshift because of the color red, which is at one extreme of the visible light spectrum for us. The concept is that a galaxy is moving away from us and sending us light in the other direction. The movement of the galaxy relative to us alters the wavelength of light, and this is how we can measure its velocity from where we are. But redshift works as a measuring tool of their velocity only if the change in wavelengths comes from its growing distance between the galaxy and us. And this is where the tired light hypothesis was made. What if the distance was not changing, in fact, but light was losing a little bit of its energy when it travels very long distance? That could explain the slight increase in the wavelength, the decrease in the frequency. Tired light was abandoned as a hypothesis because it didn't seem to work for several reasons. No loss of energy for light was ever observed or explained. And also, if this theory was right, more distant galaxies would indeed be redder. But their surface brightness seen from Earth would also be stable, and it has been observed that the brightness evolved over time, which is not consistent with tired light, and actually backs the expansion of the universe theory. and then cosmic microwave background was detected, a huge argument in favor of the Big Bang Theory, which sent the possibility of tire light into retirement. But as a question, it was a good intuition that deserved to be examined. An example of alternative cosmology that appeared in the 1960s and is now rejected by the scientific community, but was also stimulating, is called plasma cosmology. It has disappeared from labs and universities since the 1990s as a way of describing the universe, and we will see why, and now essentially survives in pop culture under the term electric universe. Electric universe proponents have in common that their rejection of pretty much all the pillars of modern astronomy, from relativity to a lot of observations that do not fit into their systems. It's a bit like a fancier version of flat earthers. Fancier because they use plenty of complicated words. But if you have even a basic knowledge of physics and watch an electric universe video on YouTube or elsewhere, you will quickly realize that it is just mumbo jumbo. It is like when the crew talks about physics and engineering in Star Trek. The words are there, it sounds like science, but it is just entertainment. The whole thing makes no sense because nothing is defined properly, and there is barely any logical connection between propositions. But let's leave this aside because initially, plasma cosmology was an ambitious attempt at challenging cosmology in the 1960s, adopting a different angle. You know what plasma is in physics. It is a state of matter, a fourth state, after the ones we are constantly surrounded by: solid, liquid, and gas. A gas is typically made of molecules or individual atoms. A plasma is like gas, but a gas of ions, that is to say, atoms or molecules in pieces. They have had one electron stripped, and 3 electrons surround them in the plasma. It takes additional energy to turn a gas into plasma. It has to be heated or subjected to a strong electromagnetic field. A property of plasma is that it is electrically conductive. It is full of free charged particles floating, so it can transport electric currents efficiently. So what did the concept of plasma cosmology mean, and why was there some pertinence to it? Because one of the question marks or problems of the modern standard model of particle physics and the theory of relativity is that they theoretically predict a similar quantity of matter and antimatter in the universe. In their language, a similar quantity of baryonic matter and antibaryonic matter, which is the same as matter and antimatter. The Big Bang should have produced a similar quantity of matter and antimatter too. But that is in theory, because in the observable universe, where is all this antimatter that, when in contact with matter, should mutually cancel themselves? It has never been found, and this is a bit embarrassing for all these models. The problem is called the matter-antimatter asymmetry, or baryon asymmetry. The question has never been solved, including today, and it was already on the table in the 1960s. One big advantage of plasma cosmology is that it provided a possible answer that would help support particle physics. Matter and antimatter would indeed be present in equal quantity in the universe, but they would be isolated in bubbles, gigantic packets that would be separated by electromagnetic frontiers. This way they would remain separated, isolated, and avoid mutual cancellation. To get there, the proponents of plasma cosmology extrapolated to much bigger scales the properties of plasma that were being studied intensively since the 1920s. Now, this theory could also integrate some of the observations made about the expansion of the universe. We would live with our galaxy and many others inside a pocket of matter bounded with electromagnetic fields. But over time, similar pockets would tend to merge like bubbles in water tend to come together to form a single bigger bubble. That could be an explanation for the apparent expansion of the universe. In this approach, what we would see would just be the expansion of our bubble of matter. As you imagine, that would be a quite big change of paradigm in cosmology. The importance of gravitation at the scale of the universe would be strongly reduced. The age of the universe, estimated by the Big Bang Theory, would no longer make sense, and standard theories about the formation of planets, solar systems, and galaxies would have it wrong, because they did not take into account the major role played by electromagnetic forces, according to the proponents of this theory. So, this was an absolutely stimulating angle to look at cosmology. But quite quickly it appeared that this approach created more problems than it solved. First, it was based on many hypotheses that cannot be demonstrated or tested. Where are these separations between bubbles of matter and antimatter? They have not been observed directly and indirectly either. There are no known traces, light, radiations, signals of their existence. The assumption that plasma can carry electromagnetic forces on extremely large scales is also contradicted by experimentation. And there is also everything that works in particle physics and relativity. If these are wrong, why all the successful predictions they made? Because it cannot be a coincidence. Plasma cosmology doesn't provide an explanation to cosmic background microwave either. So as the 70s, 80s, and early 90s passed, it appeared more and more as an intellectual construction with little to support it. The argument that existing models are not fully satisfactory, which is true, none of the standard theories about matter and astrophysics in general explain everything on all scales. The lacks or the flaws of existing theories is no proof that any alternative is right. Of course, this is why plasma cosmology and all its various ulterior iterations about the electric universe became fringe theories. They have actually never made a single cosmological prediction that could be verified, and they essentially exist as a discourse when standard theories have concrete applications that work every day. Particle physics is used in experiments all the time, and relativity serves to synchronize satellites in orbit around Earth, for example. At this point, you certainly understand why the Big Bang Theory dominates today. Scientifically speaking, it defeated other possible cosmological studies despite all its limitations. And the biggest limitation for the general public is that the Big Bang is a description of what probably happened, but it says nothing about the why, what there could be before it. Even though this question doesn't really make sense because, in the Big Bang theory's logic, time also appeared with the Big Bang. So it is absurd to wonder what there was before if time didn't exist. And the question of how it ends remains open between a never ending expansion or at some point a contraction that would lead to a big crunch. So, what happened in the early stages of the universe? According to the theory, it estimates that our universe appeared 13.8 billion years ago. For comparison, the age of Earth would be about 4.5 billion years. So our planet has existed for about a third of the time the universe has existed, based on these estimates. The first instances of the universe have been modeled based on what we know of particles, energy, and how they should theoretically behave. But obviously, there is no possible direct observation, and it is all very speculative. The universe would have appeared with the singularity, a name given to this original point because we don't have the models to describe it. Following the theory of relativity, it would have been a point of infinite density and temperature. In an instant, far less than a second, the universe went through a quick inflation, a moment of still extremely high energy density and temperature, but now cooling down, and a phase of exponential growth, so fast and powerful that the universe could have expanded faster than light at the time. In these first moments, the laws of physics as we know them would have started to work, which is a necessary assumption to model this phase. Otherwise, we would have nothing to work with. Still, during the first second of its existence, the universe would have cooled down enough for the first particles to form. First, quarks and gluons had combined to make protons and neutrons. And so, the first bricks, the first components of atoms were born. But not the atoms yet. The universe was still too densely energetic for that. The first stages would have lasted seconds, but it took hundreds of thousands of years for nuclei of atoms and electrons to combine to form atoms. These atoms were hydrogen, for the most part, the simplest and lightest kind of atom. You remember the cosmic microwave background that we mentioned repeatedly as evidence of the Big Bang. This is when it would have appeared. These newly born atoms were able to emit radiation, which since then continues through space and embedded. This is how the cosmic microwave background appeared. After thousands of years, the universe was still very young. Matter was initially distributed evenly, but over time, slightly denser regions would have appeared. These denser regions attracted more matter because of gravitation. They grew denser and formed gas clouds that, with more and more concentration, formed stars, galaxies, and all physical astronomical structures observable today. So we have seen a lot of things since our departure, when we wondered whether we could go to the center of the universe. It turns out there is probably no such place, or at least this is what the current state of cosmology points to. But instead, we found a lot of information about how humans have imagined, described, or even measured this universe and their place in it. Long before the birth of modern science, and maybe in 10 or 100 generations, our current understanding will also look very naive and lacking to our successors on Earth. We've come to the end of our little journey tonight. I hope you enjoyed this adventure, and I invite you to discover and learn more. Now you can let go and sleep, or if you're not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, good night. Sleep well.